Hello everyone and welcome to my presentation on the p-adic numbers. In part one of the presentation, we're going to develop the tools we need to get the p-adic numbers, and in doing so, we're going to see how we can get the real numbers from the rational numbers. So let's begin. The rational numbers are expressible as the quotient of two integers, and together with addition and multiplication, they form a field. So not only are there additive inverses, there are multiplicative inverses. So the first tool we need is this notion of an absolute value. So an absolute value on a field is a function which maps elements of the field to the positive rationals, and it has to satisfy these three properties here. The absolute value of 0 is 0, basically, and for every other one it would be positive. The absolute value of a product is the product of absolute values, and it has to satisfy the triangle inequality. Now, I'd just like to make this point that in part one we don't have the real numbers to work with, really, because that's what we'll end up with, where we're going to get the real numbers. This definition is really a mapping into the positive reals, but we can only use the positive rationals for now. So what's an example of an absolute value? Well, the ordinary absolute value, and it's defined in the following way. It's the absolute value of a number is that number itself if it's positive, or it's the negative of that number if it was negative. And it can be verified that it satisfies the required conditions that we had on the previous slide. The next tool we need is this idea of a metric, which is all it is a distance function. It's defined as follows. If x is a set, then a metric on x is a function which maps elements of the Cartesian product of x with itself to the positive rationals. Now all this is coordinates. So we basically look at two elements of x and look at the distance between them. It has to satisfy the following properties: that the distance from x to y is non-negative. It will only equal 0 if the points coincide. The distance from x to y is the distance from y to x, and it has to satisfy the triangle inequality. So this should look pretty familiar to our definition of the absolute value, and it's lucky in a way because it means that we can use the ordinary absolute value together with q to form a metric space. We'd write it like this, and the metric is defined in the obvious way, that the distance between 2 points is just the absolute value of their difference. The next tool we need is this notion of Cauchy sequences. So a Cauchy sequence in a metric space is a sequence whose elements become arbitrarily close to each other, and this here is the formal definition. So what this basically means is, let's say I picked epsilon was a millionth, okay, so a very small positive number. I can go far enough down the sequence such that after I reach a certain point, all the numbers are within a millionth of each other. If I chose epsilon to be a billionth, it probably means I have to go further down the sequence, but I can still do it. After a certain point, all the terms are within a billionth of each other. And the last little ingredient we need is putting the past few things together to talk about what we mean by a complete metric space. So a metric space is complete if every Cauchy sequence converges in that space. So what that means is that we look at the limits of these Cauchy sequences, and if every Cauchy sequence we can construct, the limit of those Cauchy sequences is also in that metric space, then that metric space is called complete. So as a concrete example, the rational numbers with the ordinary distance function is not complete. Why is this? Well, here's a sequence here: 3, 3.1, 3.14, etc., etc. This is a Cauchy sequence of rational numbers, but its limit is pi, which is not rational, which means by our abstract definition here, q cannot be complete with this ordinary distance function, because if it was, then the limit of this sequence should be a rational number, but it isn't. So what do we do about this? Well, we complete q to get the real numbers, and we do it in exactly the way I've just described. We'd add in the missing bits. So for example, we'd put in pi. And we do this for all the possible limits of all the possible Cauchy sequences that we can construct. And this gives us the real numbers. And it can be proven that the completion of a field gives a field, and since Q is a field, R is a field. So here's a summary for part one, a recipe for the real numbers. So really the only ingredients we needed were the rational numbers and an absolute value on the rational numbers, and we used the ordinary one. From these we obtained a metric on the rational numbers. We got this from the absolute value. Cauchy sequences with respect to this metric, We looked at all the limits of these and saw that most of them actually didn't converge in the rational numbers, so we put all those limits in, and ultimately we obtained the real numbers. So what we're going to do in part 2, now that we have all these tools at our disposal, we're going to change an ingredient and start off with a different absolute value on Q. That's exactly what we do. We look at the p-adic absolute value. So this p stands for prime. It's a placeholder. So if p was 2, it would be the 2-adic absolute value. If p was 3, it would be the 3-adic absolute value, etc., etc. So for each prime, there's an associated p-adic absolute value. So what do we do? Well, first of all, we fix a prime p. So p is fixed. And we let alpha be a non-zero element of Q. Then what we do to alpha is we factor out the powers of p in it. So n here is an integer, and g and h is a fraction in its lowest terms, and g doesn't contain any factors of p, and neither does h. So we can always do this. What this basically means is, g, h, and p are all co-prime to each other. So assuming that we've written alpha in this way, which we can always do as long as alpha is 0, and we can see we treat 0 differently in a second, we can define the p-adic absolute value of alpha. The p-adic absolute value of alpha is the p-adic absolute value of how I've written alpha. We look at this p to the n, and we say, well, the absolute value of this number is p to the minus n. Now, when I first saw this, I thought this looked a little strange, but it turns out that for each prime p, we get all these different absolute values. All of those, together with the ordinary absolute value, these are the only non-trivial absolute values that we can have on Q. So it's not random at all. It's actually incredibly natural. And in order to make this an absolute value, we have to look at what happens with 0, and we just set the absolute value of 0 to be 0, and then it can be verified that this is indeed an absolute value. And we note that unlike in the case with the ordinary absolute value, where it could be any non-negative rational number, we see that the p-adic absolute value only takes a discrete set of values. It only takes p to the n, for n is an integer, together with 0, which it is a lot different to the ordinary case. So here's just an example. If we fix p to be 11, and we look at, say, alpha is 968 ninths, then the p-adic absolute value of 968 ninths, for p is 11, is we write 968 ninths in the way we're supposed to by what we've just talked about, and we look at we see that this was 11 squared, so the 11-adic absolute value of this number is 11 to the minus 2, or 1 over 121, just by the definition. So what we do is we're just going to follow the same procedure as we did in part 1, except all we've changed is the absolute value. We're not using the ordinary one anymore, we're using the p-adic one. And what do we need? We need a metric. Well, it's going to naturally give us a metric on Q defined by this. It's the distance between 2 points is just the p-adic absolute value of one point minus the other. And this metric here is going to throw up some crazy surprises. So for example, when p equals 7, we have that 28,814 and 2 are closer together than 3 and 2 are. So ordinarily we'd think that these two numbers are far apart, and 3 and 2 are, they're only 1 apart. But let's have a look at what happens. So the distance from 28,814 to 2 is this 7-adic absolute value of 28,812, and I write 28,812 in the way I'm supposed to, 7 to the 4 times 13, and I see that the absolute value of this number is 7 to the minus 4. Is 1 over 2,401. But the distance from 3 to 2 is just 1, which is 2,401 times as big as the distance from 2 to 28,814. So yeah, that's very surprising. But what shouldn't come as a surprise is the fact that Q is not complete with respect to this metric. So just like it wasn't complete with respect to the ordinary metric, it's not going to be complete with respect to this one either. And if you remember back, I gave an example of a Cauchy sequence which tended to pi, which obviously wasn't rational. Well, I'm going to fix p as 5. I'm supposed to fix p. So let's have a look at this number here. This number here is certainly not an element of Q, but the sequence of partial sums, 1, 1 plus 5, 1 plus 5 plus 5 squared, etc., which is just this sequence here, 1, 6, 31. Well, this wouldn't be a Cauchy sequence with respect to our ordinary metric. but it is a Cauchy sequence with respect to the 5-adic metric. Indeed, we're adding on smaller and smaller and smaller bits each time. So yeah, it's pretty surprising. This number here, whatever this number is, it would be an element of the completion of Q with respect to the 5-adic metric. And that's exactly what we're going to do. And for each prime, there is a completion of Q with respect to the associated p-adic metric, the thing we've just defined. And for fixed P, we call this completion QP. So if P was 5, we call it Q5. And since Q is a field, QP is a field. We call it the field of p-adic numbers. So there are lots of interesting things I could do, but in the time I've got, we're gonna have to just focus on a couple. So the first thing I thought we should look at is how do we write down a p-adic number? Well, every p-adic number can be represented as a power series that looks like this. So this x minus m, this x minus m plus 1, all the way up to x naught, x1, x2, etc. These are just the coefficients of the power series. This is a power series in ascending powers of p, starting at some negative power p to the minus m. Now, of course, a bunch of the xi's could be 0 up to some point, or perhaps m is actually 0 and we start at x naught, or this is just the general representation of a p-adic number, and in order to see this, we look at the sequence of partial sums, and we see that this forms a Cauchy sequence with respect to the p-adic metric in Q. So this is indeed the most general representation of a p-adic number. Turns out that the representation is unique if we restrict that the xi's are in the integers mod p, so that is that the xi's are either 0, 1, 2, 3 up to p minus 1. And we call the collection of the xi's the p-adic digits, and we often write them from right to left. So this is the notation. We could either use this notation or this notation, and we can sort of interchange between them quite easily. So let's have a look at an example now. Let's say we've completed Q with respect to the 5-adic metric, and we have obtained Q5. So how do we write 0? Well, I've written this Q here and this Q5 here just for emphasis. So the rational number 0 is this p-adic number 0. 1 would be written as 1, 5 would be written as, well, we'd write it first of all as its expansion, 0 plus 1 times 5, which by our notation is just this number 1, 0. But here's what might come as a surprise. What's this number? What's minus 1? Well, it's this here. It's this number 4, 4, 4, 4, 4, 4, 4, dot, 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 going off to the left. So why is this? Well, let's have a look here at this sum. So if I take this number 1, this is just the number 1 here, and I add it to this number 4, 4, 4, 4, 4, etc. Well, 1 and 4 is 5, and then the 0 plus the 4 just gives us the 4. So we can see how this sum sort of makes sense. But the 5 is really a 1 in the next place along. So we get a 0 there and a 5 in the next column along. But then I repeat the same thing and I say, well, this 5 is really a 1 in this column. So I get a 0, 0, 5 here. And this just keeps going. And really I end up with 0, 0, 0, 0, 0, which is just 0. So this number 1 plus this number gave me 0. So what was this number to start with? It was minus 1. So there's many interesting things I can do. But in the time I've got, we're going to move on to part 3, what I'm going to be looking at sort of specifically in my project. So we're going to look at the geometry of QP. So R and QP are both metric spaces. And this, Q is a metric space with respect to the ordinary absolute value. It's a metric space with respect to the p-adic absolute value. And when we complete Q, we get R and QP are metric spaces as well with respect to their metrics. But they're very different. Now I have one last definition for everyone. In a metric space, the open balls are the sets that look like this. The ball, center A, radius R, is all the points that have distance less than R away from A. So this distance, of course, depends on the metric, right? That is what the metric is. So in R, we have that the ball center A radius R is all the real numbers x, such that the distance from A is less than R, which is just these open intervals. But in QP, we get something totally different. They take the form, this is just the definition, But since R only takes these discrete set of values p to the n, we have the following geometric interpretation of the open balls. So let's say this big circle here on the outside represents R is 1. Then we have 3 balls inside, radius a third. And maybe the blue one is the one that starts at a 0, the red one is the one that starts at a 1, and the orange one is the one that starts at a 2. And then inside each of these balls radius a third, we have the balls radius a ninth. And then inside each of those is the ball's radius a 27th. And of course, this big ball, this ball, the radius 1, is actually contained alongside 2 other balls inside a ball radius 3. And what we get is the graph, is a graph that looks like this. So say the vertex in the middle is this big circle, then the vertices that go off to the right and to the bottom left are, say, the balls contained within it, and the vertex which goes off to the top left is the one that is connecting it to the ball in which it's contained. So that's maybe that can be a little difficult to see, but essentially this goes off in all directions, infinitely, and it can be shown quite easily to be isomorphic to this graph here, this tree. I mean, they're both trees, but this one looks a lot more like a tree, I would say anyway. And at each level, we get the different possible radiuses. And what I'm looking at in my project is transformations of p-adic numbers. In particular, ones like x goes to ax plus b. And that any transformation of a p-adic number is going to do something to any set of p-adic numbers, in particular these open balls. So if the transformation sends balls to balls, so if it preserves, if there's some kind of preservation there, it'll have some effect on the tree. It'll send vertices to it should send vertices to vertices and edges to edges, and that is exactly what I'm going to be looking at in my project. But I've unfortunately run out of time. So thank you very much for listening, and have a nice day.